Thanks a lot for inviting me. So we're going to hear about EP for, I think, the fourth time in the last 48 hours. I'm sorry about that, but it's actually an interesting algorithm. So my view on EP is that it's very simple. It just takes a long time to explain. So I'm going to go, step by step through the various ingredients you need to build a successful implementation of expectation-propagation. I'm going to focus today on the classical case of doing GLMs or more specifically logistic regression. And today I'm going to talk a bit more about recent developments in EP and some promising directions which are not completely mature. So today, the stuff that we know works, tomorrow the stuff that might work but is interesting nonetheless. Okay, so here's, you've heard about directional inference from Christine's talk. I think they fall on a spectrum that goes from methods that are fast and not so accurate to methods that are slow and a lot more accurate. I think on one end we'd all agree that VB and Laplace are very fast. So for example, in the case of VB, you can take a method like latent Dirichlet allocation, which I've used quite a bit. It's a very simple algorithm when you use the VB form. It's very fast. I mean, it's a method for doing essentially mixture models on documents, on discrete objects. And you can crunch through thousands and thousands of documents in a few seconds. So it's very fast. It gives you a point estimate that's quite good. But the uncertainty you get, like the estimation of the error bars, is completely useless. And people don't use it in practice. But it's very fast, and you'd be hard-pressed to do anything with EP in such a case. So that's one end of the axis. I think Laplace is around here somewhere. Where it is in relation to VB depends on the exact problem. Now you have a new class of methods that are called stochastic variation inference, which is essentially minimizing the KL divergence, just like in VB, just like Christine explained, but in more complicated cases where you have to sample. And using a Gaussian as the approximating family. And now you have EP, which tends to be quite accurate, a bit slower, and it's also usually more work to implement. Okay. So EP is actually not so new. It was introduced by Minka in 2001. It's quite popular in machine learning. It's less popular in statistics, I think, because statisticians are, on average, less comfortable with dirty approximations. Everyone thinks to be exact. But it's getting more popular, I think. And one of the reasons is that it's known empirically to be very accurate in many cases. For example, in the case of Gaussian processes, Gaussian process-based models, like Gaussian process classification, it's almost exact. Logistic regression, almost exact. And one advantage of EP is that it's very easy to parallelize, and it's fast when implemented properly. Okay. So just a reminder on the objective, and Christine's already mentioned it. We have a posterior distribution I'm going to call pi of theta, theta being the parameters. We wish to approximate it with a Gaussian distribution, so EP can be done with non-Gaussians, with more complicated exponential families, but focus on Gaussians here. And what we want to minimize is the KL divergence from pi to q. So before in variational Bayes, we had q to pi, now we have pi to q. The reason we might prefer going from pi to q is that it's an expectation under pi, and it forces your approximation to have the support at least as wide as the true distribution. So you're trying to cover the mass of your actual target. Okay? And another property that's nice with the KL divergence in this direction is that it's moment matching. So if you minimize the KL divergence over Gaussians, then the optimum, I think as Guillaume mentioned, is the Gaussian with the same moments as the target. So essentially it's a way of computing the mean and the covariance of the target distribution. Now, this is, of course, entirely intractable. If you could compute the mean and the covariance of your target distribution, you could just do that. So this objective is a theoretical objective. It's not something that we can actually work with. So in order to work with it, we have to approximate it. So the way we approximate it in EP is to replace it with, instead of one big global problem, you replace it with simpler local problems that we can actually solve. Now here's a big picture view of EP. Imagine that we're in distribution space. So this is the space of probability distributions. I'm representing it as Euclidean space, of course, completely non-Euclidean. So this is just a picture, right? It's not a proof. Q is the space of Gaussians. So it's a constrained subset of all possible distributions. And for example, the initial approximation might be a specific Gaussian called a Q1. Your target distribution is outside the space of Gaussians typically, otherwise you wouldn't be doing that. And what you want to do, ideally, is to project your target pi onto Q. Because that's just the minimum, the point on Q that has the minimum distance to pi. So ideally, you're doing a KL projection. Now, we can't do that, but thankfully, beyond the space of Gaussians, there's a margin, a neighborhood of not too horrible distributions. Okay, so pi might be very bad, but the space between Q and pi contains something that's still relatively tractable. So it's the same idea as in SMC, sequential Monte Carlo. You go from a complicated distribution to a simple one, from simple distribution to complicated one step by step. Except SMC would, move from Q1 to something here, somewhere here, and hopefully down to pi. But EP is going to project back to the space of Gaussians over and over again. So what you do is you introduce the hybrids between the initial approximation and your target distribution, and the hybrid is within the space of tractable distributions. Okay, so you sort of interpolate between the two, project back to the space of Gaussians, and that is your new approximation, call it Q2. And of course, you can then introduce a second hybrid between Q2 and pi, project back, and so on and so forth. And hopefully, if everything goes well, you're going to reach a stationary point. That's the projection of pi onto Q. This works beautifully in Euclidean space, of course. And in the space of distribution, it's not so simple. But it's a nice picture to keep in mind to understand what EP is trying to do. OK, so you've seen this a few times. Of course, the posterior distribution, as usual, has independent data points, so we can write it as a product of a prior and a bunch of likelihood sites. They're called sites in EP jargon. So we're going to have n+1 sites, the first one corresponding to the prior, and every other site corresponding to bits of the likelihood function. Now we're going to approximate this posterior with a product of Gaussian factors. So we're going to have n+1 Gaussian factors. What I think confused a few people yesterday is that, unlike in VB, you're not making the assumption that the approximate distribution factorizes over different bits of theta. So you're not saying that there's some independence in Q. You're just saying that Q is a product. But here, there's no index on theta. I'm taking a Gaussian distribution that's not going to have any independence. It's going to be typically, everything is going to covary with everything else. So it's a very different approximation than what you see in VB. So I have a product of Gaussian factors. For my Gaussian factors, I'm going to use slightly different notation. I'll get back to that than the one you typically see, which would have like a mean and a covariance. All my Gaussian factors are going to be written as, of course, they're still quadratic, but it's AI here is a precision matrix. And RI doesn't really have a name in the literature, so we decided to call it a linear shift, because that's what it does. It sort of shifts the distribution. If you take these Gaussians and you multiply them as to get the global approximation, then all the AIs and all the RIs, they just add. So they're a very convenient way of parameterizing these distributions because they become additive. I'll get back to that point. So it's just my my way of writing things down. So essentially EP, you take a product of Gaussians to form the global approximation. Now, if you remember, I told you that there's sort of a margin of not intractable distributions between the target and the Gaussians, and the way we produce elements of that margin is to hybridize the approximate distribution and the true distribution. And we hybridize by taking out one approximate factor and putting in a real one. Okay? So just, I remove one of the approximate factors. So instead of taking the product of all the i's, I remove one. Or this should be q minus j, sorry. So I remove the j factor, and then I'm going to introduce the true factor instead. This is how I interpolate between the current approximation and the target. So the global approximation minus one of the sites is called a cavity, because it's sort of you've created a hole, okay? And the cavity times the true site is called a hybrid, because it involves bits from the two different distributions. So you take out the approximate factor, you insert the true factor, you get the hybrid. And so hopefully, we have a hybrid that's closer to the true distribution than our current approximation. Now, the next step, if you remember from my picture, is to take H1 and bring it back down to the space of Gaussians. And we do this using the KL divergence. And doing this using the KL divergence just means matching the moments. So all I need to do at this point is compute the moment. So I'm going to need a normalization factor because my hybrid distribution contains a likelihood, so it's not normalized. So this is just like a small marginal likelihood, if you like. So the z, and then I need the expectation over the hybrid. So it's just theta times the hybrid divided by z, integrated over d theta, and then I need a covariance. So I'm just computing 3 moments, a moment of order 0, a moment of order 1, and a moment of order 2. And that gives me a new Gaussian with these moments. Okay, and that's my new Gaussian approximation. I've projected back to the space of Gaussians. So here, the last step would be, I've taken H1, and then we're back onto Q. So let's say we do this on a simple one-dimensional model. My current global approximation is a Gaussian, which appears here in dotted lines. If I remove one of the factors, I'm going to get something that has higher variance, because one of the factors stands from some of the data, and typically data will reduce variance. Okay, so I remove one of the factors, I get a Gaussian with higher variance. This is, I'm going to call this Q minus 1, it's the cavity. I introduce a likelihood factor. Okay, so this is a non-Gaussian bit. I take the product of the hybrid, of the cavity and the likelihood factor. That gives me a hybrid. The hybrid is a lot more Gaussian than the likelihood because we introduced a Gaussian pseudo-prior. And because it's a lot more Gaussian, typically it's going to be more tractable, and I can compute the moments. If you have questions, you should stop me. Okay. Now, the last step is a tiny bit more complicated. I think I need better notation to introduce it, so I'll just briefly explain what it does, and then I'll get back to it later. So the last step is, so remember, now we have new moments for global approximation. So we need to update the approximation for the site. Okay? So we know that by taking a hybrid of the previous global approximation and one likelihood site, we change the mean and the variance in some way, okay? And so this is the Gaussian effect of this likelihood site. And the way we get this Gaussian effect is that we find the Gaussian bit, qi, such that q minus i, which was our cavity, times the new qi, has the same moments as the hybrid. Okay, so we find a way of moving in the right direction. It sounds complicated, it's actually a simple linear operation than the natural parameters, so more on that later. So I've stayed at a very abstract level, and I'm going to try and work through a concrete case of doing logistic regression. So you've seen this a few times already. I'm going to say that my data is actually, well, they're binary, so the outcomes are binary, but I'm going to write them down as -1, 1. The covariates are a big matrix n times p, so I have p predictors and n data points. And the model is that p of y equals 1 given xi and theta is phi of xy transpose, sorry, yeah, this guy, phi of xy transpose theta, and phi is the logistic function. So it's a GLM, it's a classical logistic regression, there's nothing fancy about it. So first we have to choose a factorization. We're going to assume that we have a Gaussian prior, so we don't need to bother with it much. This can be relaxed, so we don't actually have to have a Gaussian prior. The target distribution is the prior times n likelihood sites. And I'm not going to change anything, I'm just going to use this natural factorization as the factorization for EP. EP is more flexible, you could do other factorizations, but I'll talk about that tomorrow. In this simple case, we're just saying, well, my posterior distribution already comes in as a natural product, and I'm going to use this factorization. So you have n plus 1 sites, L0 being the prior, and each site is a likelihood, and a likelihood is just a sigmoid along some dimension of the thetas. So, what about the hybrid, though? If you remember the hybrid, it's my cavity prior, so cavity prior is Gaussian, times a likelihood site. And the likelihood site in this case is a sigmoid. So, you know, you might be saying, Simon, this is nonsense because we, you know, a Gaussian times a sigmoid is a nasty distribution. There's nothing we can do about it. But actually, it's not true. There's the distribution turns out to be tractable for a reason that's often overlooked in, when people introduce EP. So I'll spend a bit more time than what people normally do explaining why the hybrid distribution is actually tractable. So, you know, we have a sigmoid times a Gaussian. It doesn't appear to be tractable, so we could, of course, be doing MCMC to compute the moments, which would be a bit silly, because then we're back to using MCMC. But we don't need to. There's something called the linear subspace property that's going to help us. So let's start with the normalization constant. That's the first thing we need to compute. So we have a Gaussian times a logistic likelihood along just one dimension. So the z is the normalization constant, and it's just phi, which is my sigmoid, yi xy transpose theta, so this is just a linear function of theta, times a Gaussian term, so n of theta with a certain mean and a certain covariance. And this can just be expressed as an expectation under the cavity prior, right? It's just the expectation of phi of yi xy transpose theta under the cavity prior. Now, because it's just an expectation, it's expectation of this bit here, which is just a one-dimensional variable, actually. So if you take theta, you take its dot product with yi xi, you get a one-dimensional variable, and you're just computing the expectation of one-dimensional variable, which tells you that you're back to a one-dimensional case. So instead of having to compute moments over an n-dimensional, sorry, p-dimensional distribution, which would be very difficult, actually you can do all your computations on one-dimensional marginals. So in this case, all you need to do, you know, if yi xi equal this b, you have a new variable that you call b transpose theta. It's called this u, and u is Gaussian because it's just a linear sum of Gaussians. It stays Gaussian. I'm just computing the expectation of some nonlinear function of a Gaussian. That's easy. I can do this using numerical integration. So this is for z. Seeing what happens for the other moments, remember we need the mean and the covariance as well. To see what happens with the other moments, I'm actually going to use the blackboard. I'm just going to do it for the mean because the covariance requires a bit more notation. But to see what happens with the mean, all you need is times lemma. So if you have a Gaussian distribution I'm going to pretend it has zero mean. So if you have a multivariate Gaussian distribution, or actually make it, just I'm going to make my life simpler, assume that it's a standard Gaussian distribution with mean zero, and the identity matrix is the covariance. If you're trying to compute a moment of the form expectation of you have this nice relationship, it's called Stein's lemma, and it's just integration by parts for Gaussians. Okay? So what this says is that if you're trying to compute the expectation of f of x times x, all you need is the expectation of the gradient of f. So how is that useful? Well, it's useful here because if you look at the what would happen over there if I were to compute if I have to compute theta phi of yi xi transpose theta times some Gaussian term, and I'm assuming here the Gaussian term is a standard Gaussian, just to make my life easier. Well, you recognize this as f of x times x. Okay? So all I need is the expectation of the gradient of this. And because it's the expectation of the gradient, and because it's still a linear function coming in here, then all I need is the one-dimensional marginal. Okay? Because I'm back to the trick I had with the z. Okay? So to see what happens in complete generality, you can also look at, essentially, you replace this trick for the moment. If you want to generalize it, you can just use the moment generating function. You realize that if you put in the moment generating function, you can apply this trick for any moment. So that gives you a very general proof of this linear subspace property. So to summarize, we're able to compute z and the mean and the covariance using just one-dimensional marginals, because they're just one-dimensional marginals over a Gaussian. All you need is quadrature. Very generally speaking, I think it's worth spending just a few seconds on this, because it's what makes EP possible in many cases. So, and also, it's used in EP, but it's such a nice property that I'm surprised it hasn't been used anywhere else. Well, at least I don't know about it. So if you have a likelihood that can be written down as BI, so GI, some nonlinear function of BI theta, and BI is a matrix that just summarizes theta along a few dimensions, so it has lower dimensionality, it's a projection. So if you have like a likelihood that only depends on a few linear dimensions, then all the moments you need can be computed based on a marginal that has fewer dimensions than p. Okay, so all you need, so if BI goes from p to k, so from p dimensions to k dimensions, all the moments you need can be computed based on marginals of dimension k. So this gives you some kind of, Christian was talking yesterday about some row blackwization, and this is a kind of row blackwization. You can compute your moments on distributions of lower dimensionality. And it's absolutely central to the success of VP.
So that works for the Gaussians, but...
Oh, Gaussian prior, yeah.
Yeah. Gaussian approximation, no? It only works for the Gaussian approximation, like for more general exponential families. It doesn't...
Oh no, it doesn't work for more exponential. So absolutely, this is just this depends on Stein's lemma, on the properties of the Gaussian. Yeah, you're right. This is just under Gaussian priors.
Stein's lemma works outside Gaussian.
Yeah, but it doesn't.
But not with the mean and the variance.
Exactly. So you couldn't play the same trick. So if you like, what happens, let's do the moment generating function trick if you like, but if you, what happens is this. If you have a moment generating function, which is going to write it as oops. This is your Gaussian prior. This is your likelihood that only depends on a few linear dimensions, so A of theta, and this is your moment generating function. What happens is that exponential theta transpose x, you can just stick that into the Gaussian. And if you stick that onto the Gaussian, that gives you a new Gaussian, and you can play the same trick, right? Because then you can take the marginal of A of theta. And so you're back to moment generating function of dimension k rather than dimension p. And I don't see a way of doing this in...
It works for mixtures on the lines of Gaussians.
Okay. You'll have to explain that to me later, but it's sort of a side point, so maybe we should...
Yeah.
Okay. Now, I don't know how many people here use R, but for the people who use R, this is the main step then in the EP algorithm. So it's something I wrote a few days ago. It all boils down to that. So if you want to compute the hybrids, what you do is you write a function that it's called compute moments log it. It takes an outcome y, a mean and a variance of a Gaussian. So you compute, you declare a function that takes the product of a Gaussian times a logistic. You integrate it over minus infinity to plus infinity to get z. Then you modify it a bit. So you take f of x times x to get the mean, f of x times x minus the mean squared to take the variance, and you return that. And this is your this is where you spend most of your time when you do EP, and it's just that. Okay, it's you're all computing moments over one-dimensional distributions. So in order to give you a better view of the algorithm, I'm going to spend the next 4 or 5 minutes giving you a bit more details on exponential families because it lets us write down EP in a very compact manner. So it's an idea that's originally due to Matthias Seeger, I think. And it's worth our time, I think. Because it also lets us generalize EP to non-Gaussians, to other exponential families. How does this work? Well, if you take a Gaussian, in the form I had earlier, you realize that this can be written as this bit is just the sum over all the aij's, so all the indices in the matrix of a product of theta I and theta j divided by 2. And this is just a linear sum again. So one very compact way of writing this Gaussian is to have a vector function, s of theta, which equals theta 1, theta 2 divided by 2, theta 1, theta 3 divided by 2, and so on. So all the second order stuff, and then all the linear stuff. And you take the dot product of this with lambda, where lambda is a vector version of A and R. Okay, so you can put all the parameters together in one big vector. So one corresponding to the to a vectorized form of the precision matrix, the other one corresponding to the linear shift, and you get something that's in the form of an exponential family where S of theta are the sufficient statistics and lambda are the natural parameters. That's the usual way of writing down a multivariate Gaussian as an exponential family. Now, why is this nice? Well, I have like one single parameter instead of two, so that's going to make my notation a lot more compact. And in some sense, they're the natural parameters of the Gaussian. And the natural parameters have their counterparts, which are moments. And the moments are the mean and the covariance. And you notice that the mean, if S of theta gives you all the just products of the form theta 1, well, theta I, theta j's, and then all the theta 1 to theta n, then the expectation of these second order and first order functions of theta are just going to be the mean and the covariance. So that's my moment parameterization. Okay, so for Gaussians as natural families, you can express each Gaussian as either a mean and a covariance, that's the moment parameterization, or you can express them as precision and shift, that's the natural parameterization, and there's a one-to-one way of mapping between the two parameterizations. So the precision is just the covariance inverse, and the shift is the precision times the mean. So I'm going to write this as eta are the moment parameters, lambda are the natural parameters, and v of eta takes a moment parameter and gives me a natural parameter. It's actually not free. I mean, this transformation is something that you have to be careful with in EP because inverting matrices is expensive. So that's one subtle point that you need to watch out for when implementing EP. If you have more than a handful of parameters, well, more than 100, it starts becoming expensive to do all these matrix operations and computing transformations from precisions to covariances. If you have less than 100 parameters, you don't really need to worry about it. So, why do we bother with this? Well, we bother with this because if you have sites that can be expressed like this, okay, so it's just a product of summary statistics transpose site parameters lambda I, well then, if you take products, everything adds. So, adding all my bits of Gaussians together just produces a sum over the lambda i's. Forming a cavity meant taking out a site. And taking out a site meant dividing, as Guillaume explained yesterday. It's much more convenient if you can just subtract. So if we take my global distribution, which is the product of all the QIs, we divide by one QI, we get our same summary statistics, lambda minus lambda I. So to take out the effect of a site, you just subtract from the natural parameters. Very simple. And this allows me to actually give you the whole EP algorithm in just one slide, which is very nice. So how did this work? Well, EP just starts out by initializing site parameters. So per site, you have one set of natural parameters. Call them lambda 1 to lambda n. And then a global parameter, which is just the sum of all the contributions from all the individual sites. And EP just does the following. If you haven't converged yet, you loop over the i's, you form a cavity, okay, lambda minus I, which is your big global lambda minus the effect, the contribution of a single site. You create a hybrid formed by the cavity prior, which is just this, lambda minus I inside this Gaussian expression. You add the likelihood, this is your hybrid. Now you compute the moments. I'm writing it in this form, so it's expectation over the hybrid distribution of the sufficient statistics, which in this case are just theta and theta transpose, if you like. And I get moments which live in the world of moments. So I'm going to call this eta I. Now what we need to do is, because we write this in natural parameters, we need to take the moments, transform back to natural parameters. Okay, so that's eta nu of eta I. And this gives me my new contribution of the site. So it's the new precision and shift of the hybrid minus what I had before. Okay, because lambda minus I is just a cavity. And this gives you my new approximation. So this somewhat complicated idea of finding the Gaussian that's going to give you the right mean and covariance becomes very simple natural parameters. It's just you take the new precision and shift you have for the hybrid, and you subtract what you had from the cavity, and this is your new contribution of the site. Yes?
Don't you need a variance as well?
Oh, it's all in lambda. So lambda contains the precision and the shift. So if you convert it to moment parameters, it's a very compact way of writing things. I could put this into 2 slides with Q's and R's and so on, but this generalizes to any exponential family you like. Okay. So EP in one slide, form cavity, form a hybrid, compute the moments, transform back to natural parameters, and then you just update the global approximation. It's the cavity plus your new side contribution. That's it. That's EP. Yeah. I'm sorry, where? Oh, sorry. Yes, you can write it like that as well. Yeah, absolutely. It cancels out. Yes and no. So the linear subspace property comes in again, and it turns out that you can do all this using low rank operations. So you don't need full rank inverses. It would take a while to explain this, but roughly speaking, what happens is that one other aspect of the linear subspace property is that the mean and the covariance are only modified again along the subspace that is non-Gaussian, which gives you low rank operations. It's a beautiful property, but it takes a while to prove. So if you have like models in which at each iteration you only update a linear subspace, then you get away with low rank operations. So our global approximation is then this Gaussian here with the sum of the contributions from each side. And one nice way of thinking about it is that each bit of the likelihood at the end of the day contributes a little bit of precision, a little bit of additional precision, and a little bit of shift. So the role of each part of the likelihood is to shift you towards a certain part of the space and add precision. That's what likelihood is supposed to do. Okay? And forming a cavity just removes that contribution from the global approximation. Okay, so what do we have in terms of expensive operations to make this realistic? So we need to compute moments of the hybrid. We need to do this for each site. That's completely unavoidable. So this is an order of n operation per complete pass over the data. So at each step, you introduce one data point. A whole pass over the data is going to be n. And this is typically the expensive bits in EP. It's computing moments.
Can I ask a question?
Yeah.
So what's n and what's p for me?
Oh, so.
The dimension of the whole sequence S and then it's p squared or something.
Okay, so in my notation, E is the number of data and n is the number of data points, and p is the number of parameters. So this computing the moments of the hybrid, if you're lucky, like in a GLM, because we've used the linear subspace property, it doesn't depend on p anymore. So it's O(n), because we still have to do this n times because we have to go through all the data, but it's independent of p. But you're doing quadrature, so it's not free. This is what makes EP slightly slower than Laplace, for example. Quadrature is more expensive than just taking gradients. But it's O(n), so it scales very well, actually. Then we need to transform the natural parameters to moment parameters, and that involves a matrix inverse. So if you're doing this the naive way, you compute the regular matrix inverse. So in the end, you end up with complexity npq per complete pass over the data, which isn't bad for p small. Okay, so for p small, the cost is dominated by n. And you don't need to worry about the matrix operations so much. For p large, it becomes interesting to worry about them. And as I said, over 100, it becomes worth it doing the low rank operations I talked about. No, this is per pass over the data. So, if you remember the overall algorithm, it said while we haven't converged, we're going to loop over all the i's, so all the data points one by one and so on. So the question is, how many times do we need to do that? Well, we don't know. We have no good theory on how many passes you could need. For sequential EP, which is the algorithm I've talked about here, what you notice is that in a typical GLM, you go 3 times over the data, maybe 4 times tops, and you've completely stabilized. So, and it doesn't seem to depend on n. So this tells you that the overall guess for the complexity of EP is order of n, which is very good scaling in n. Better scaling would be log n, but n log n, but O(n) is not too bad. Okay. So, to be honest, I had a demo prepared of EP in logistic regression, but I missed the right adapter for my laptop, so I can't show it to you. So you have to trust me that it works. If I can get my shit together, I should have it ready for you tomorrow. But in the meanwhile, the question is, oops. Why did people get excited about EP? And well, the reason is that it actually works very well in GLMs. And one sort of GLM is Gaussian process classification, which is just non-parametric logistic regression. So that instead of having just a parameter set that's of size p, your parameters are of size n. It's semi-parametric. You're trying to essentially, it's very similar to adding splines. So it's non-parametric logistic regression. And there's a paper from 2008 by Nikesh and Rasmussen, which is very well cited because they found surprising results. So if you do Gaussian process classification and you try a number of different approximations, you can look at the quality of the estimates you get for the mean and for the covariance. And what they found is that in some cases, the Laplace approximation gave you terrible estimates of the mean. So this is, the y equals x line should be where the points are, and it's really not. So in this case, Laplace gives you terrible approximations. VB does a bit better, but EP is essentially exact. Okay, the same, and if you now look at the sort of estimates you get for the covariance, if you remember the theory bit that Guillaume talked about yesterday, Guillaume mentioned that EP and Laplace should have an approximation of the covariance that's almost as good. Okay, you don't get an order of magnitude. You get an order of magnitude in estimating the mean because EP shifts in the right direction. But you don't get an order of magnitude estimating the covariance, and that's what you see here. You do, it gets better for EP than for Laplace, but it's not the same, quite the same effect as for the mean. So the mean is nearly exact. You get a wee bit of error on the covariance, and VB is terrible. And VB is terrible because of this zero avoiding property that Christine mentioned. That VB is gives you variances that are severely underestimated. So they would need to be scaled up quite a bit. On the other hand, VB is very fast, much faster than EP. So EP does very well, and generally speaking, in latent Gaussian models. So GLMs with Gaussian priors, there's an extensive comparison between EP and various forms of Laplace and so on in this paper by Sek and Heskes, 2011. It does very well with logistic regression with various priors. So I haven't talked about it, but if you have non-Gaussian priors, then they're just additional sites. And because typically they only depend on one component of the thetas, you can approximate them just the same way. So you can deal with non-Gaussian priors, and that's the paper by James and Nicolas, where EP does very well. EP also does very well in sparse models, where you try to squeeze some of the coefficients down to 0. So essentially, again, GLMs or linear models, and you squeeze some of the coefficients down to 0. If you don't have too many parameters, then EP does very well. Otherwise, the linear algebra just gets horrible. And you don't want to go there, but if you have on the order of 1,000 to 10,000 parameters, then you get very good performance out of EP. And there's many more. I mean, EP has been used in robotics for optimal control. It's been used in bilinear models. It's been used in all kinds of machine learning stuff.
Can I ask you a question?
Yes.
So when you have like latent variables,
Yep.
how does it work? Like,
It doesn't. It does. Then use VB. It depends. Okay. So you don't have to. So you can still use EP for mixture models. Ulrich Paquet and Manfred Opa have done that, and they get good performance out of it. But you don't introduce the latent variables. So you just your parameters just the mean and the covariance of the Gaussians.
And when you say good performance, it's on par with Gaussian base or better, or conditions?
Well, you get a if you compare to MCMC, you get a better estimate for the log marginal likelihood and so on.
Okay.
I don't know about predictive performance. I don't remember the results.
But at least you avoid this problem with Gaussian base of having a too small support.
You avoid that, but then. Okay, so the question is actually complicated. So one thing I'm curious about with respect to variational Bayes is that I saw a poster at NIPS just a few months ago showing that EM in mixture models has very good properties as an optimization tool because it avoids local minima. So EM just gives you an upper bound over the function you're trying to approximate, you're trying to minimize. And the upper bound has this nice property that it sort of swings over local minima. So that's why EM works so well in mixture models. It doesn't get stuck in the very shallow local minima because they don't appear in the upper bound that you're minimizing with EM. I'm wondering if the same thing doesn't apply to VBEM as well, where VBEM doesn't get stuck in very shallow local minima. It's just speculation on my part. So I don't know. Honestly, I don't know. I don't think there's been an extensive comparison of EM and VBEM and EP in mixture models. There's just one. There's the one paper, and the reason there's just the one paper is that it's horribly complicated to implement. So by all means, use VBEM in mixture models. Because what you need to do is use the Gaussian Wishart as your exponential family. So it's the product of a Gaussian times a Wishart. And the moment computations become very complicated and so on. So Manfred loves doing complicated computations by hand, so it's good for him, but I don't think anybody else really wants to go there.
Okay. So if VB is much faster,
Yep.
that gets you a good point estimate for the mean.
Yes.
And if the variance is well approximated with Laplace, why don't you mix the two and then you get something good?
You could do that. Absolutely. I don't think anybody's done it, but you could do that. The question is, if you center the at the EM estimate, the VBM estimate, and take the Hessian there, maybe it's good. Nobody's tried it. There's again at NIPS there was a paper on improving on VBM, like getting better covariance estimates, and so the solution is a local perturbation, and that could put it on par with EP. We don't know yet. The corrections are also available for EP. So EP could potentially then gain another order of magnitude. We don't know. Okay, so oh yes, one last thing that would be interesting to people here is that EP can be used to speed up MCMC by quite a lot actually. So one thing that was mentioned by Nicolas is that you can use EP as your basis for doing importance sampling. So the approximation is good enough that you can just use it as a basis for importance sampling, it works. There's a nice paper by Maurizio Filippone and Mark Girolami from last year, where they do something, they use EP in, to form approximate marginals, and use that as a proposal for MCMC, essentially. It speeds up inference in Gaussian process models by a lot. So because EP gives you good approximations, it also gives you a way of exploring in posterior distributions in efficient ways. So it can be combined with MCMC if you like. Okay, so this is the bit where I have to be honest and tell you about all the potential difficulties you're going to encounter with EP. when I talked about it to Ulrich Packe, who's another person who's worked a lot on EP, he mentioned that EP is very nice, but it's only used in a large-scale application in one place, and that's Microsoft for the Truescale player rating system that was designed by Minka, who's the creator of EP. And that's the only known wide-scale application of EP in industrial settings. I mean, there may be ones we haven't heard about. If, Minka, I'm sure, can do magic with EP, but he's not like the rest of us. So Truescale is very nice. It scales over tens of thousands of participants. That's just one example. So the question is, why don't people use it more? So one reason I think is that it's very hard to prove anything much about EP. So that, unlike GIP samplers, so that might have stopped some people because it's slightly uncomfortable when you can't say how good your approximation is. Also, I think EP can work extremely well, but implementation requires a lot of care, especially in complex models. You have to be careful about all that stuff. So the implementation cost can be quite high. So why? Because we can have stability problems. EP is a fixed point algorithm, so just do the updates until you reach a fixed point. The updates don't change anything anymore. And occasionally, especially on models that are not concave, EP doesn't stabilize, it diverges. And Guillaume mentioned that yesterday. You get EP just blows up, essentially. So one of the causes is that your covariance matrices, because they're the sum of inverses of precision matrices and so on, they accumulate noise until one of the eigenvalues goes to 0 or to minus something, and then you can't do your linear algebra anymore, and it doesn't make sense to have covariance matrices with negative eigenvalues. So one thing to keep in mind when implementing EP is to use stable linear algebra operations. So don't do explicit inverses of covariance matrices. Use Cholesky, for example. Do you all know that trick, or am I speaking Chinese, as you say? Okay, so if you just use in MATLAB, for example, if you just call solve, it's not a very stable operation. Your numerical errors tend to build up. If you do all the operations using Cholesky, much more stable. Zeger has lots of details about this. The second fix is if you do get divergence, you can try slowing down the iterations. So this means that if lambda prime would be the update suggested by the algorithm, you don't go all the way. You go some way between lambda t, which is your current approximation, and the suggested one. So you slow it down. So there's some theory on why this helps. But also an interesting open question, we don't know the optimal rate for slowing down EP. We don't know if there's a way of doing it adaptively, and we don't know the optimal parameterization in which to do the slowing down, because you can do it on natural parameters, you can do it on moments. We don't know any of that. So if somebody has some ideas on how to do this, it would be extremely helpful, I think. A last fix is something called Power EP, and it's a clever idea, again, by Minka, of course. It's a form of likelihood tampering. What you do is you say, well, EP diverges because the likelihood is too strong, and it pulls me in different places at once. I don't want that. So another way of slowing down EP, if you like, is instead of having n sites that are full strength, so to say, you divide them to make them weaker. So you re-express your posterior as the product of all the lambda i's to the power of 1 over k over n and over k. So artificially, you divide a single site into k bits by taking powers. And power EP seems to behave a lot better on hard models. And there's a fork theorem that says that it's equivalent to minimizing KL of QP in the k tends to infinity limit. So you get back to variational Bayes, which is more stable. I'm saying it's a fork theorem. Guillaume hasn't been proved yet.
I still haven't found somebody who's written down a true proof. Maybe there exists one.
Okay, so it's it's a conjecture that's very likely to be true, I think. But not proved yet. But it seems to relate EP and VB. So if you slow down EP in this very particular way, you get back VB, and VB tends to be more stable. It's actually provably stable in log concave cases. Okay. There's some implementations that you can play with. Okay, very quickly. So some stuff in MATLAB. There's a new R package by James that does logistic and probit models. There's no complete black box implementation of EP yet. If you want to learn more about it, you can. It's worth looking at different perspectives on EP because I've just shown one, and they're all quite interesting. So you can look at Minka's original paper, which tells the story of EP as improved assumed density filtering. There's a set of lecture notes by Manfred, which has links to statistical physics. Other forms of variational inference you can find in the book by Wainwright and Jordan, Minka 2005, and the cleanest notations in Zega 2008. I think that's the best way to learn EP. It's, I mean, at least it's the one that's helped me the most. I'm going to stop here for today. Thanks a lot.
Okay, except for Judith, anyone ask questions? Sylvia?
I just wanted to ask you, imagine you've got a spatial distribution, so there's no natural, factorization.
Yep.
Would people block, do some kind of, start with some kind of intuition about, how to define these products by block where the dependence go down or something like that? Is there work in that line?
Yeah, there is. There are connections to message passing. I think Guillaume mentioned that yesterday as well. You can write down EP as a message passing algorithm, and so you can divide your posterior into cliques and so on. You can do all these tricks. You can also use EP to fit approximations that have tree-like dependencies. So this would be your new approximating family. It's something that has tree-like dependencies, and so it might help you. There's something that's very surprising as well. So I've only talked about. Sorry, if I can just take a minute. This is a beautiful result, which I wouldn't have time to talk about otherwise. But Manfred has this idea with the Ising model. The Ising model is a distribution over binary strings, right? So it's just 0 and 1, 1, 1, 0, 0, so on. And you write it as -1/2 of the sum of xi, aij, xj. And this is P of x. And the Ising model is just a distribution of a binary strings. It's exponential family. It's not normalized. Manfred says, well, you can take this distribution, you can view it as a Gaussian, which doesn't seem to make any sense. Of course, formally it's a Gaussian, but it can only be -1 or +1, or -1 and 0. 1 and zeros. But if you can write this as a Gaussian times a set of indicators which force all your x's to be either -1 or +1. Okay? So each site in this case, you apply EP, and each likelihood site is something that forces your variable to be either -1 or +1. It works beautifully. We have no explanation as to why this works at all, but it gives you very good moment estimates and a good estimate of the log cumulant function and so on.
Where is that written?
I'm sorry?
Where is that written up?
Where is what?
Published.
I'll dig it up for you. It's in one of Manfred's paper. I think the one on corrections to EP. Yeah. So it doesn't have to be a division of a factorization according to likelihoods.
Further questions?
Thank you. So you mentioned slowing down the moves with this factor alpha. That seemed kind of similar to stochastic gradient descent. So can you reduce the alpha and get some convergence results by appealing to that?
Okay. The difficulty here is that EP doesn't really have a cost function we feel comfortable minimizing. So yes, I mean it looks similar to stochastic gradient descent. You can write, you can find some kind of function that has fixed points that are the same as the fixed points of the EP algorithm. Whether it makes sense to minimize it is more questionable, because people have tried that, and you get to fixed points that are as good as the ones you get using the normal algorithm. So it's also what makes EP difficult to analyze, is that it's not standard optimization where you write down an objective and then you minimize it.
Any further questions? You can still ask them tomorrow, actually. Okay, thank you.
Thank you.